SpaceX just scored a massive victory at Pad 2. Their flame trench system unleashed a torrent visible from miles away, proving the future of Starship launches is here. But there's a problem. S38 completely failed its static fire test, sitting cold while engineers scrambled to figure out what went wrong. No frost on the tanks means no fuel loading, a ground system failure that could derail Flight 11's timeline. Let's dive right in. On September 13th at Starbase, SpaceX achieved something remarkable. Their Pad 2 flame trench system activated at full power, sending torrents of water cascading skyward in a display visible from miles away. This wasn't just a test. It was proof that SpaceX has solved one of rocketry's toughest challenges: how to build infrastructure that can withstand the extreme forces of the world's most powerful rocket. The dual bucket flame trench design represents years of engineering refinement. Unlike Pad 1's water-cooled steel plate system, Pad 2 uses a more sophisticated approach that disperses heat and pressure through two separate channels. This system is engineered to handle 10,000 tons of thrust repeatedly, the kind of punishment that V3 and V4 Starships will deliver. This success matters because Pad 2 isn't just another launch platform. It's the blueprint for every future Starship facility worldwide. When SpaceX builds launch pads at Cape Canaveral, on the Moon, or eventually Mars, they'll use Pad 2's proven design. The September 13th test validates an entire generation of launch infrastructure that will support humanity's expansion into space. Just 5 days after Pad 2's triumph, reality delivered a harsh reminder of space industry realities. September 18th was supposed to mark another milestone: S38's static fire test, clearing the path for Flight 11. The schedule looks straightforward: a single engine test followed by a 6-engine firing that would prove S38's readiness for flight. Instead, engineers watched their carefully laid plans crumble. The tank farm vented normally. Technicians completed their pre-test checks. The chopsticks moved into position exactly as planned. Everything appeared perfect until the critical moment. Fuel loading began. That's when nothing happened. No frost formed on S38's tanks, the telltale sign that cryogenic methane and liquid oxygen were flowing into the vehicle. No matter how long they waited or how many times they cycled the systems, S38 remained stubbornly dry. The test scrubbed without a single engine firing. The technical evidence points to a complete ground system failure. Either the fuel lines developed blockages, the transfer pumps malfunctioned, or the connections between Pad 1 and the temporary ship test system failed entirely. This represents a fundamental breakdown in the most basic requirement of rocket testing: getting propellant into the vehicle. The S38 incident exposes something more troubling than a single equipment malfunction. It highlights the growing strain on SpaceX's ground systems as they push for unprecedented launch cadence. The ship test system, while innovative as a temporary solution, introduces complexity that creates new failure points. Every time SpaceX transitions from booster testing to ship testing, engineers must reconfigure multiple fuel line connections. Each reconfiguration increases the chance of leaks, clogs, or connection failures. What was once a reliable process at the dedicated Massey test site has become a complicated juggling act at the operational launch pad. This pattern isn't new. Flight 10's first launch attempt scrubbed due to similar ground system issues. The common thread is clear. While SpaceX's rockets advance rapidly, their support infrastructure struggles to match that pace. The very speed that makes SpaceX innovative also creates the conditions for preventable failures. The closure of the Massey test site, driven by resource concentration on operational pads, now appears short-sighted. That facility provided dedicated, streamlined ship testing capabilities. Its loss forces SpaceX to rely on improvised solutions that fail at critical moments. These ground system problems couldn't come at a worse time. While S38 sits grounded, the first V3 components are taking shape. Booster B-18 nears completion in Mega Bay 1, representing the most significant Starship upgrade in the program's history. V3 introduces transformative capabilities: Raptor 3 engines delivering higher thrust and efficiency, hot staging that eliminates the need for explosive separation, redesigned grid fins for better aerodynamic control, and new catching points that will enable ship recovery alongside boosters. The payload capacity jumps from V2's 35 tons to over 100 tons, enough to establish permanent bases on the Moon or Mars. Beyond V3 looms an even more ambitious goal, V4, standing 142 meters tall with 42 engines generating 12,300 tons of combined thrust. V4 is designed to carry over 200 tons to orbit. This is the rocket that will build Mars cities and ensure humanity's survival as a multiplanetary species. But these revolutionary vehicles mean nothing if SpaceX can't fuel them reliably. The same ground systems that failed S38 must work flawlessly when V3 and V4 carry their first payloads, and eventually their first human passengers. While SpaceX battles fuel line problems, China's space program advances with methodical precision. Their Tianwen-3 Mars sample return mission targets a 2028 launch, with Earth return by 2031. NASA's equivalent mission won't return samples until 2040 at the earliest, hampered by budget cuts and technical delays. This creates an opening that China is positioning to exploit. If SpaceX can't resolve their ground system reliability issues, America's technological advantage in space could evaporate. The nation that establishes reliable, frequent Mars transportation will dominate space commerce, resource extraction, and potentially human expansion beyond Earth. The implications extend beyond national prestige. Mars likely holds answers to fundamental questions about life in the universe. Recent NASA discoveries suggest that ancient Martian rocks may contain fossilized evidence of microbial life, potentially the first proof that Earth isn't unique in hosting biology. NASA's Perseverance rover recently photographed rock samples with unusual leopard-like patterns, white streaks surrounded by black borders that could represent fossilized biological activity. These samples, sealed in tubes and waiting on Mars, might contain the most important scientific discovery in human history. But there's a problem. NASA can't retrieve them. Budget constraints and technical delays have pushed their sample return timeline to 2040. China could beat them by nearly a decade. SpaceX, with a functional Starship, could return these samples by 2029, if they can solve their ground system problems. The irony is striking. The most advanced rocket ever built sits meters away from the most sophisticated launch infrastructure ever created, yet both are rendered useless by failing fuel pumps and clogged lines. The difference between advancing human knowledge and watching China claim the greatest scientific prize in history may come down to basic industrial engineering. SpaceX's solution requires both immediate fixes and long-term structural changes. In the short term, they need complete ground system redundancy. If one fuel line fails, backup systems must activate automatically. This isn't revolutionary technology. It's standard practice in industries where reliability matters. The long-term solution demands dedicated ship testing infrastructure. Whether that means reopening Massey or building new facilities, SpaceX must end their dependence on improvised pad-switching operations. Reliable space transportation requires reliable ground support. There's no way around this basic requirement. SpaceX has the engineering talent and financial resources to implement these solutions quickly. Their track record of rapid problem-solving suggests they'll address the S38 failure within days or weeks. The September 19th test window provides their first opportunity to prove the fixes work. The S38 failure serves as a crucial reminder that space exploration demands different standards than Silicon Valley's move fast and break things philosophy. Software failures can be patched with updates. Rocket failures can kill astronauts and destroy billion-dollar missions. As SpaceX prepares to carry humans to Mars, reliability becomes paramount. The ground systems that couldn't fuel S38 must work perfectly when human lives depend on them. From this perspective, discovering these problems during unmanned tests represents a valuable lesson rather than a catastrophic setback. The contrast between Pad 2's success and S38's failure perfectly illustrates SpaceX's current challenge: revolutionary engineering achievements undermined by preventable operational failures. They can design systems that catch falling rockets, but struggle with basic fuel transfer operations. This duality reflects the company's rapid growth and ambitious timeline. Traditional aerospace companies spend decades perfecting systems before operational use. SpaceX iterates in real time, accepting failures as learning opportunities. This approach enables incredible innovation, but also creates the conditions for frustrating setbacks. The next few months will determine whether SpaceX's Mars timeline remains achievable. B-18 awaits its first tests. S-39 components continue stacking. Pad 2 needs final validation before taking over primary launch duties. V-3's debut flight targets December, but only if ground systems demonstrate consistent reliability. China watches every SpaceX setback, knowing that American delays create Chinese opportunities. Their methodical approach may lack SpaceX's innovative flair, but it offers something equally valuable: predictable progress toward clearly defined goals. The fundamental question isn't whether SpaceX can reach Mars. Their rockets prove that capability exists. The question is whether they can do it reliably, safely, and before competitors claim the prizes that matter most. S-38's fuel failure represents more than a technical setback. It's a warning that the basics matter as much as the breakthroughs. Success requires mastering both revolutionary rocket design and mundane fuel pumps. SpaceX has proven they can achieve the first. The second challenge now demands their full attention, because the future of human space exploration may depend on getting it right. What's your take on this fuel system failure? Is it a minor hiccup in SpaceX's Mars plans, or does it reveal fundamental problems that could derail their timeline? Drop your thoughts in the comments and hit subscribe to stay updated as this space race unfolds. This is exactly why the S-38 fuel failure matters more than any rocket explosion ever could. When SpaceX's Starships blow up during flight tests, that's expected. They're pushing boundaries. But when basic ground systems fail to deliver fuel, that reveals something far more concerning: the gap between revolutionary engineering and operational reliability that could determine who wins the race to Mars. What this means is that SpaceX stands at a crossroads. Pad 2's success proves they can build infrastructure for the future. S-38's failure proves they haven't mastered the basics of the present. The company that catches rockets with mechanical arms struggles with fuel pumps, and that contradiction will define whether humans reach Mars in this decade or the next. This moment connects directly to humanity's greatest goal: becoming a multiplanetary species. Every fuel line that fails, every test that scrubs, every day that slips pushes that dream further into uncertainty. While SpaceX perfects their ground systems, China methodically advances toward Mars sample return. The nation that solves reliability first won't just win bragging rights. They'll control humanity's next evolutionary leap. The next 90 days will reshape space exploration forever. B-18 awaits its first cryogenic tests. Pad 2 needs final validation. V-3's debut flight targets December. Each milestone builds toward the ultimate prize: reliable Mars transportation that makes Earth's backup planet accessible to everyone, not just the lucky few. By early 2025, we'll know if SpaceX fixed their ground system problems or if they're still fighting the same reliability battles. We'll see if V-3 delivers on its promise of 100-plus ton payloads. Most importantly, we'll discover whether SpaceX's Mars timeline survives contact with engineering reality. What do you think will happen first? SpaceX solving their fuel system problems, or China announcing their Mars sample return mission timeline? The answer might determine which flag gets planted on Mars first. This is Space Hub, where we dive deep into the engineering challenges that will define humanity's future among the stars. If you want more analysis that connects today's technical setbacks to tomorrow's space breakthroughs, hit subscribe and join the conversation that's shaping our species' next chapter. The race to Mars isn't just about rockets anymore. It's about who can make space transportation as reliable as commercial aviation, because that's what it takes to build civilizations beyond Earth. What if SpaceX's Dragon could beat China to the moon? While NASA burns $5.2 billion per Artemis launch, experts reveal Dragon's 9.5-ton design crushes Orion's bloated 26.5 tons. Dr. Zubrin dropped a bombshell. Dragon could reach lunar orbit using Falcon Heavy, slash costs by 90%, and launch monthly instead of yearly. But here's the catch. It needs modifications NASA never saw coming. As China races ahead, could Musk's Dragon Gambit be America's secret weapon? Let's dive right in. Here's what nobody wants to admit. NASA's Artemis program is bleeding money faster than a punctured fuel tank. Every single launch costs American taxpayers $5.2 billion. That's not a typo. That's the price tag for getting 4 astronauts to lunar orbit and back. Meanwhile, China's Chang'e missions are advancing methodically, and their next crewed lunar mission could happen sooner than anyone expects. But what if there's a backdoor solution hiding in plain sight? Let's talk cold, hard physics. SpaceX's Crew Dragon weighs 9.5 tons. NASA's Orion? A whopping 26.5 tons. That's nearly 3 times the mass for essentially the same job. Dr. Robert Zubrin, founder of the Mars Society, put it bluntly, Dragon isn't just cheaper than Orion, it's vastly superior because it's vastly lighter. This isn't just about weight, it's about efficiency. Every kilogram matters when you're hauling mass 240,000 miles to the moon. While Orion struggles under conflicting NASA requirements from multiple administrations, Dragon was built with one clear purpose: get humans to space efficiently. Here's the engineering brilliance. Dragon has 50% more internal space than the Apollo capsule, while weighing only 20% more. That's smart design beating bureaucratic bloat. So how do you actually get Dragon to the moon without building entirely new rockets? This is where SpaceX's existing hardware becomes the game changer. Falcon Heavy already exists and launches payloads regularly. The solution is elegantly simple. First, Dragon launches with crew on a standard Falcon 9 rocket to low Earth orbit. Separately, a Falcon Heavy launches, carrying a fully fueled upper stage. These two vehicles rendezvous in orbit, where the Falcon Heavy upper stage becomes Dragon's lunar taxi. This upper stage handles everything: trans-lunar injection to get to the moon, lunar orbit capture, and the trans-Earth injection burn for the return journey. It's like having a dedicated space tug for lunar missions, using hardware that already exists. The critical question: can Dragon actually survive a lunar mission? The flight to the moon and back takes at least 6 days, pushing Dragon beyond its typical International Space Station missions. Dr. Zubrin calculated the life support requirements with precision. One crew member consumes roughly 1 kilogram of oxygen per day.